Representation Theory of Finite Groups, Lecture 3, Simple Modules and Schur's Lemma. Let us start with a quick recap and description of our setup. So we always work over the field C of complex numbers. In what follows, G denotes a finite group and V a finite dimensional complex vector space. A G-module structure on V is given by realizing each element G in G as a linear operator on V, such that the group operation in G corresponds to the composition of linear operators. A homomorphism from a G-module V to a G-module W is a linear map phi from V to W, which intertwines the G-module structures on V and W. And G-mod with little m denote the category of all finite-dimensional G modules. So as usual, we have the natural notions of submodules, quotients, direct sums, and the kernel and the image of a homomorphism. Let us now define simple modules. Let V be a G module. We will say that the G module V is simple, provided that it is non-zero, and the only submodules of V are 0 and V. An alternative terminology using representations, simple modules are the same things as irreducible representations. So here's an analogy with number theory. Recall that a positive integer p is called prime, provided that it is not equal to 1, and the only divisors of p are 1 and p. So this is an explicit analogy. So simple modules are very similar to prime numbers, and the definitions are very explicitly similar. So here is a trivial example. Every G module V of dimension 1 is simple because it is non-zero, it has dimension 1, and it only has as subspaces the 0 subspace and V itself. So any G module of dimension 1 is simple. So we denote by IRR of G, so irreducibles of G, the set of isomorphism classes of simple G modules. Here is a more advanced example. The claim is that the defining two-dimensional module over the dihedral group D2 times 3 is simple. So recall that D2 times 3 is a group of symmetries of the regular triangle inscribed in the unit circle in R2, such that one of the vertices of this triangle is the point 1, 0. And the defining D2 times 3 module is defined using this definition and extending the scalars to the complex numbers. Let us choose the standard basis E1, E2 in R2. And the same vectors are, of course, the standard basis in C2 as well. So here is a picture. So our unit circle, triangle, and the standard basis vectors E1 and E2. So the group D2 times 3 has 6 elements, and it is generated by the following two symmetries. So first of all, we can rotate triangle by the angle 2 pi over 3, and we can reflect it with respect to the symmetry axis given by E1. So this is a reflection in the vector E2. So E2 goes to minus E2, and the orthogonal complement of E2 stays the same. So the matrix of the reflection then is as follows. So the reflection with respect to E2 preserves E1, so E1 goes to E1, the first column is 1, 0, and it sends E2 to minus E2. So the second column of the matrix is 0, minus 1. And the matrix of the rotation by 2 pi over 3 is a matrix consisting of cos 2 pi over 3, sine 2 pi over 3, minus sine 2 pi over 3, and cos 2 pi over 3. So this is 1/2 of the matrix minus 1, root of 3, minus root of 3, minus 1. Note that our module has dimension 2. So if it were not simple, it must have one-dimensional submodules. However, the only one-dimensional subspaces invariant with respect to the first matrix are the linear spans of the first and the second basis vectors. So this is because the basis vectors are eigenvectors for the first matrix with different eigenvalues. Any invariant subspace of dimension 1 is of course given by an eigenvector. This matrix has only two eigenvectors up to scalars, and these are the linear spans of E1 and of E2. However, none of these is invariant with respect to the second matrix, and we are done. So therefore, there are no one-dimensional invariant subspaces, and our defining module over D2 times 3 is simple. So here's a negative example. Observation: the regular module over G is simple if and only if G consists of one element. Indeed, if G consists of one element, then the regular module is one-dimensional and hence simple. If G consists of more than one element, then we saw that the linear span of the vector in the regular module given by the sum of all elements in G is a submodule of the regular module. So this is a submodule which is non-zero and which is not equal to the whole module. So the regular module is not simple in this case. Similarly, the natural Sn module, the linearization of the natural action of Sn on the set 1, 2, 3, and so on up to n. So this module is simple if and only if n is equal to 1. If n is equal to 1, then the module is one-dimensional and hence simple. If n is greater than 1, then we have already seen that the linear span of the vector in this module given by the sum of all elements 1 plus 2 plus 3 and so on plus n is a one-dimensional submodule. Again, we have a submodule which is not zero and which is not the whole module. So this natural Sn module is not simple if n is greater than 1. Now let us formulate and prove the main result of this lecture, which is called Schur's lemma. Theorem called Schur's lemma. Let V and W be two simple G modules. Claim 1. If V is not isomorphic to W, then the space of G homomorphism from V to W is the zero space. Claim 2. If V is isomorphic to W, and phi is a non-zero G homomorphism from V to W, then phi is an isomorphism. Claim 3. If V is isomorphic to W, then the dimension of the space of all G homomorphisms from V to W is 1. And claim 4, if V is equal to W, then the space of G endomorphisms of V consists of the scalar multiples of the identity map. Let us now proceed with the proof. So let V and W be two simple G modules, and phi a G module homomorphism from V to W. We know that the kernel of phi is a submodule of V, but V is simple, so it has only two submodules, 0 and itself. So the kernel of phi must be either 0 or equal to V. If ker of phi is equal to 0, then phi is injective. If ker of phi is equal to V, then phi is equal to 0. Furthermore, the image of phi is a submodule of W. But W is simple, so the image of phi is either 0 or the whole of W. Consequently, phi is either 0, so it is if the image of phi is 0, or is surjective if the image of phi is W. Putting these two things together, we get that phi is either the zero map or is an isomorphism. And this proves both claims 1 and 2 of Schur's lemma. Here is the recollection of these two claims. If we have two non-isomorphic simple modules, the only G-Hom between them is 0. If they are isomorphic, then any non-zero Hom between them is an isomorphism. Let us now proceed to the proof of the last two statements. So assume that V is equal to W. As we have already seen, the identity map is certainly an endomorphism of V. Consequently, Any scalar multiple of the identity map is also an endomorphism of V, because endomorphisms form a linear space. Let phi be an endomorphism of V. Since we work over the complex numbers, phi, it's an endomorphism of a finite dimensional complex vector space. It has an eigenvalue. Let's call it lambda. So here it is very important that we work over the complex numbers. Then we can consider the linear transformation phi minus lambda identity V. So phi was an endomorphism, lambda identity V was an endomorphism. So this linear transformation is a G endomorphism of V. However, the kernel of this linear transformation is non-zero because lambda was chosen to be an eigenvalue of phi. So this is a definition of the eigenvalue. But we have only two options. Any endomorphism is either zero or an isomorphism. So if the kernel of an endomorphism is non-zero, the whole endomorphism should be the zero map by claim 2, which means that phi is a scalar multiple of the identity. So this proves claim 4, and claim 3 follows directly from claim 4. Here are some remarks. If dimension of V is 1, then the space of all vector space endomorphisms of V is already one-dimensional. And hence, in this case, any vector space endomorphism of V is a G endomorphism of V. Remark 2. If the module V is isomorphic to a direct sum of two non-zero modules, then we can construct the following two endomorphisms of V. So we can project the direct sum onto the first component and then embed it back into the direct sum. Or we can project the direct sum onto the second component and then embed it back into the direct sum. Note that these two endomorphisms are linearly independent, for example, because their images, so V1 and V2, have zero intersection. So they are non-zero subspaces and they have zero intersection. So this endomorphism must be linearly independent. So in particular, it follows that the dimension of the endomorphism algebra of such a direct sum is at least 2. Now let us talk about the semi-simple modules. A G module V is called semi-simple, provided that it is isomorphic to a direct sum of simple modules. Alternative terminology, semi-simple modules are the same thing as completely reducible representations. Remark 1, the zero module is semi-simple. By convention, it is isomorphic to the empty direct sum of simple modules. And each simple module is semi-simple. It is a direct sum with one summand. And also a direct sum of semi-simple modules is semi-simple, always. So here is a small notation. If X is a G module, then X to the power direct sum K denotes the direct sum of K copies of X. So directly from the definition, which have that each semi-simple module is isomorphic to the direct sum L1 to the power direct sum K1 plus L2 to the power direct sum K2 plus and so on, plus Lm to the power direct sum Km, where L1, L2, and so on Lm are pairwise non-isomorphic simple G modules. This allows us to define the notion of a multiplicity. Let V be a semi-simple G module. So then we can write V in the decomposition as on the previous slide. So it's a direct sum of copies of pairwise non-isomorphic simple G modules. So the number Ki in this decomposition is usually called the multiplicity of the simple module Li in V. So if some simple module does not appear in this decomposition, then one says that the corresponding multiplicity is 0. And here's an important proposition. The multiplicity of a simple module in a semi-simple module is well defined, which means it does not depend on the choice of the decomposition of this semi-simple module into a direct sum of simple modules. So the definition of a semi-simple module only guarantees existence of a decomposition into a direct sum of simple module. It does not say anything about any kind of uniqueness. So this proposition gives uniqueness for this decomposition in some sense, which we will specify now. So from this proposition, it follows that a decomposition of a semi-simple module into a direct sum of simple modules is unique up to an isomorphism and permutation of summands. So in other words, if we have two such decompositions, so we write V as a direct sum of simples x1, x2, and so on xl, and as a direct sum of simples y1, y2, and so on ym, then L is equal to M, and there is a permutation sigma in Sm such that xi is isomorphic to y sigma of I. So this is the explicit version of this uniqueness statement. Before we can prove the proposition, we need to talk about the additivity of taking Homs. Lemma: if U, V, and W are G modules, then the space of all G homomorphisms from U to the direct sum of V and W is isomorphic to the direct sum of the space of all G homomorphisms from U to V and the space of all G homomorphisms from U to W. Proof: recall that we have the following homomorphisms. We have embedding of each of the components of the direct sum into the direct sum, and we have projections of the direct sum on each of its components. Clearly, if we first embed and then project back on the same component, we get the identity map on that component. And if we first embed and then project onto a different component, then we get 0. So now we can consider two maps between the different sides of the isomorphism which we want to prove. If we take a linear map phi, which is a G homomorphism from U to the direct sum of V and W, we can map it to the vector where the first component is pi V after phi, and the second component is pi W after phi, and this will be an element in the direct sum of G Homs from U to V and G Homs from U to W. Conversely, if we have an element psi from this direct sum, written in the form psi V psi W, then we can send it into the sum of IV after psi V and IW after psi W, and we get an element in the G Hom from U to the direct sum of V and W. So using these properties of projections and embeddings, it follows that these two maps are mutually inverse bijections. And similarly, one shows that for any three G modules U, V, and W, the space of G Homs from the direct sum V plus W to U is isomorphic to the space of G Homs from V to U plus the space of G Homs from W to U. Now we are ready to prove our proposition. So we want to prove that the multiplicity of a simple module in a semi-simple module does not depend on the choice of a decomposition. So let V be a semi-simple module written as a direct sum of simples with the corresponding multiplicities. We just choose one way to decompose V in this way. And let L be a simple G module. Let us consider the vector space of all G Homs from L to V. By the additivity of the Hom which we just proved, so this vector space is isomorphic to the vector space given by the direct sum over all summands I from 1 to m. Then we take the space of all G homomorphisms from L to Li and to the power direct sum Ki copies. However, by Schur's lemma, the space of G Homs from L to Li is either zero-dimensional if they are not isomorphic, and it's one-dimensional if they are isomorphic. So the dimension of the space is exactly Ki. So in other words, we managed to interpret our multiplicity using some invariant which certainly does not depend on the decomposition. Our invariant is the space of all G Homs from L to V, and this has nothing to do with the decomposition. And this space gives us the corresponding multiplicity. So this gives us the following idea how to understand all semi-simple G modules. So semi-simple G modules are direct sums of simples, and such decompositions are unique. So if we want to understand semi-simple G modules, we need to understand simple modules, which is usually a difficult problem. And then we can form their direct sums. It's a very easy construction. So at this stage, however, we don't know much about simple G modules. For example, we don't even know if there are finitely many simple G modules. So we will learn much more and find out that there are only finitely many simple G modules later on in this course. So let us look at an example. Consider the natural Sn module given by the linearization of the natural action of Sn on the set 1, 2, and so on n. And the claim which I want to prove now is that this module is semi-simple. The case n is equal to 1 is very easy, we already discussed it. If n is equal to 1, this module has dimension 1, therefore it is simple, and so it's also semi-simple. So in the case n is equal to 2, we already know that this module is not simple. It has a submodule given by the element 1 plus 2. So here the trick is we can consider this element 1 plus 2 and another element 1 minus 2, and these two elements of course form a basis in this module. It's not the standard basis, but it is some basis. And in this basis, the action of the elements of S2 is given by the following matrices. Of course, the identity element in S2 acts via the identity matrix. And the transposition 1, 2, so if we apply 1, 2, then U of course goes to itself. So the first column is 1, 0. While W, it's 1 minus 2. If we swap 1 and 2, we will get 2 minus 1, which is minus 1 minus 2. So W goes to minus W. So the second column of the matrix is 0, minus 1. But now we readily see from the matrices that we have a decomposition into a direct sum of one-dimensional subspaces. So if we consider the subspace given by the first basis vector U and the subspace given by the second basis vector W, then both are one-dimensional subspaces invariant under the action. So they are both submodules and also simple submodules, and the whole module is a direct sum of these two. So V2 is a semi-simple module. Let us now talk in more detail about the case n is equal to 3. So consider V3 and consider the following new basis in this natural module. So as the first basis vector, we take 1 plus 2 plus 3. The second basis vector is 1 minus 2, and the third basis vector is 2 minus 3. And consider the subspaces of the module given by W and by U1 and U2. We already know that W is a submodule, and it is a simple submodule because it has dimension 1. So we claim that U is a submodule as well. So the symmetric group S3 is generated by the transpositions 1, 2 and 2, 3. Let's compute how they act on the elements U1 and U2. So 1, 2 swaps 1 and 2, so it sends U1 to minus U1. And it sends U2 to 1 minus 3, which is U1 plus U2. So 2, 3 sends U1 to 1 minus 3, which is U1 plus U2. And it sends U2 to minus U2. So in particular, both these transpositions send the elements U1 and U2 to elements in U. So it means that U is a submodule of V3. And from this calculation, we already have the matrices of 1, 2, and 2, 3 acting on U in this basis U1 and U2. So the matrix of 1, 2 is column-wise minus 1, 0, 1, 1, and the matrix of 2, 3 is 1, 1, and 0, minus 1. So now we claim that U is a simple module, which will prove our claim because V3 is W plus U. W is simple. If you prove that U is simple, then V3 is semi-simple. So we claim that U is a simple module. Since it has dimension 2, if it were not simple, it would have a one-dimensional submodule. So the matrix of the action of 1, 2 on U has two eigenvalues, 1 and minus 1. So here is the matrix, it's upper diagonal, so eigenvalues are on the diagonal, minus 1 and 1. The eigenvector for 1 is 1, 2, easy to check. So if we multiply with 1, 2, we get 2 minus 1, 1, 0, 2, 2. So 1, 2 is an eigenvector for 1, and 1, 0 is the eigenvector for minus 1. This is straightforward to check. At none of these vectors is an eigenvector for the matrix of 2, 3. So for example, if we take 1, 2 and apply this matrix, we get 1 minus 1, not a scalar multiple of 1, 2. So this means that none of the eigenvectors of the first matrix is an eigenvector for the second matrix. So there are no one-dimensional invariant subspaces, which means that U is a simple module. And since V3 is a direct sum of U and W, it follows that V3 is semi-simple. Finally, let us consider the general case in a quick, sketchy manner. So consider the case n greater than or equal to 2. So let W be the linear span of the element W given by the sum of all elements in the standard basis of the natural module. And we know that W is a one-dimensional and hence simple submodule of Vn. So define Un as a subspace of Vn generated by all vectors of the form I minus j, where I and j are elements in the standard basis of the natural module. So clearly Un has a basis given by the elements 1 minus I, where I goes from 2 to n. We denote this element by Ui. So in particular, the dimension of Un is n minus 1. And we claim that Un is a simple Sn module. So if we can prove that claim, then again we will have that Vn is a direct sum of Un and W. Both are simple, so Vn is a semi-simple module. So it remains to prove that Un is a simple Sn module. It follows directly from the definition of Un that Un is a submodule, because if we apply a permutation to the element I minus j, we will get the element sigma of I minus sigma of j. So this is really a submodule. So we only need to check that it is simple. Okay. Let us note that the linear span of all Ui's, where I range from 2 to n minus 1, in Un is isomorphic to Un minus 1 as Sn minus 1 module. Again, this follows directly from the definition. We forget the letter n. So idea is that let us do induction on n. We already checked the basis of this induction. N is equal to 2 and 3 is already done. So the idea for the induction step, we assume that n is greater than 3 and take some element v in Un. We want to show that the minimal submodule, which contains v, is the whole of Un, which would mean that Un is a simple module because any element in v generates the whole of Un. So it is enough to show that the submodule generated by v has a non-zero intersection with Un minus 1. Because then we can do induction, we can apply the inductive assumption. By the inductive assumption, then we would have that our module Un contains 1 minus 2, and using the action of Sn, we will get all basis elements in Un from the element 1 minus 2. So let us prove that if we take a non-zero vector, then the minimal submodule contained in that vector has a non-trivial intersection with Un minus 1. So of course it's enough to assume that the starting vector doesn't belong to Un minus 1 because otherwise there is nothing to prove. And the fact that it doesn't belong to Un minus 1 means that the coordinate of this element at Un is non-zero. So the transposition of n minus 1 and n in the basis UI has the following matrix. Its identity everywhere up to the last two elements, which are swapped. If you consider the element V minus the image of V under this transposition, from this matrix it follows that this element has the form avn minus 1 minus avn for some a. Let us assume that a is non-zero, so this V prime is non-zero. So if V prime is non-zero, then if we apply to V prime the transposition n minus 2, n minus 1, and subtract V prime, we get the element avn minus 2 minus avn minus 1, and this belongs to un minus 1. And this is exactly what we wanted to prove. So the only problem we would get if the a here is 0. But the a here is 0 if and only if the last two coordinates of the vector v in our basis coincide. So now we again do induction. Now we assume that the last two coordinates of v coincide, and we apply similar arguments to the transposition n minus 2 and n minus 1. And we again solve the problem or run into a new problem, but now when the last three coordinates of v coincide, and so on. So when we go all the way, we will have only one problematic case, and this is when we have the vector v, which has all coordinates the same. So all coordinates of v is the same non-zero number. But then that vector will not be an eigenvector for the transposition of 1 and 2. So a non-zero linear combination of v and the image of v under 1 and 2 will be an element of un minus 1. And this is exactly what we wanted to prove. So let us finish with some problems and questions. Question 1. Prove that for n greater than 3, the defining d2 times n module is simple. Question 2. Prove that the multiplicity of a simple module L in a semisimple module V can be computed as the dimension of the space of all G homomorphisms from V to L. Question 3. Prove that the left regular representation of Z2 is semisimple. Question 4. Prove that a direct summand of a semisimple module is semisimple. Question 5. Write down all details in the inductive argument on the last slide of the lecture. That is, on this slide. So the induction which was rushed through here at the end. Thank you very much, and see you next time.